Hello and welcome back to CS165. Nasa 6th week na tayo, so ibig sabihin next week na yung exam natin. And ito yung second installation ng database design part. The first part is about entity relationship diagrams to tables, and then for this particular week, ang gagawin natin is to assess, given yung mga tables na yon, kung maganda nga ba yung nagawa natin na schema. And if hindi siya maganda, ano yung gagawin? So, we will introduce the concept of normalization and decomposition. So, I think we can start. The first question that we need to ask is that, given a table, gaano ba kaganda yung table na yon? And we will define what the good relational design is by showing a not so good relational design. So, suppose we have two tables, instructor and the department. In the instructor, meron tayong originally blue, and then for the department, we have originally the department name, building, and then the budget. So suppose we produce the natural join between the two tables, we can have, let's say, the in_dep, and this represents the natural join of the two relations. Bakit kaya yung ginagawa? Probably dahil most of the time, we would like to get the department of the instructor, and we wanted to minimize the calls for the natural join. So, ang gagawin natin, suppose, ay we remove the instructor, we remove the department, and we just keep the instructor department, just so we can have a list of all of the instructors with their corresponding department details. So, one thing that we could notice in this particular example or particular table is that there is repetition of information. So if you look at the department side, so yung computer science Taylor 100,000 part is repeating. So that is true for all the computer science instructors. So makikita nyo yan kay Katz, kay Srinivasan, and kay Brandt. Okay? So all the information, including the budget and the building of the department name, is repeated. So the problem here is that whenever we wanted to update a content, like the particular budget for the department, nag-increase siya to 200,000. If we wanted to update that information, we need to update all possible instance of the ComSci Taylor 100,000 para maging ComSci Taylor 200,000 na. And then, this could be a source of data inconsistency if hindi nangyayari yung ganong instances. So, it could be a source of data inconsistency if nagkamali yung magra-write sa database at isa lang yung maa-update niya na record. Another drawback of this design is that if we add, let's say, a new department with no instructor, suppose may bagong department and then mag-create ng building for it with a specific budget. Suppose magkakaroon na tayo ng data science department, and then magkakaroon siya ng building na ang name ay Alumni Engineer Centennial Hall. And then ang budget ay, let's say, 200,000. To include that specific record in the department, we can insert one record in this table with null contents dun sa ID, name, and salary. So, since wala pa naman initially instructors na nakalagay doon sa department na yun, magkakaroon tayo ng null values. So, there are two things that we wanted to avoid if we wanted to have good relational design or a good schema. Number one is that dapat walang repetition, hindi dapat magkaroon ng data redundancy. And then, second is that we wanted to remove yung mga chances na we can have null values. So to avoid having those repeated information in the resulting table or in our table, what we need to do is to decompose the schema into parts. So, yung goal natin is that wala nang repetition and wala nang null values. However, not all possible decompositions are good. So suppose we decompose the employee schema into two parts. The first part is the employee with attributes ID and name, and then the second table is employee 2 with name, street, city, salary. So they have a common attribute name. So if we have two employees with the same name, medyo problematic kapag nag-join tayo between the two tables. So, ang mangyayari dito is that we can have what we call the lossy decomposition. So, here's an example. If we have the same table as shown a while ago, we have ID, name, street, city, and salary with name Kim, for example. And then, there are two tables from the decomposition with ID, name, and then name, street, city, salary. So, naturally, pwede naman talaga that you will separate the ID and the name of the employee, and then yung other information about the employee such as salary and address ay hindi na part nung another table. However, the problem with choosing name as their common attribute is that if you perform natural join, since natural join assumes that name is equal to name ng other table and it utilizes yung mga same value for it to merge the records, then we can have something like this at the end. So we will have this as a result of the natural join, which is not equivalent to our original table because our original table only consists of two records, pero dito mas marami ka ng information. Okay, so what we need to do here is to identify ano nga ba yung magandang type of decomposition. Okay, so we have what we call the lossless decomposition, and formally we say that a particular decomposition of R, that is parang R sub 1 and R sub 2, is a lossless decomposition if this holds. So this is just a relational algebra expression explaining that if you perform the natural join between the resulting table and the first table is projecting the relation using R sub 1 set of attributes, and this one is another table resulting from projecting the table using the R sub 2 set of attributes, and then you perform natural join, then you can get some R. Okay. Ito may typographical error to, dapat this one is equivalent to R na hindi italics. Okay. And conversely, a decomposition is lossy if we have the original version or the original table undecomposed na subset lang, proper subset of the resulting table from the natural join of the two projected tables or decomposed tables. So to illustrate the formal definition in our previous slide, we have here a very simple example. Suppose we have a set of relation with attributes A, B, and C, and then we decided that we will decompose the set of attributes to set 1 containing A and B, and then set 2 containing B and C. So in this particular example, if we just divide or decompose the original matrix, ito yung projection niya sa AB and then projection niya sa BC. If you perform the natural join, then you can get this one. So this is a lossless decomposition because the R here is equivalent to this one. So to the result of the natural join of the two decomposed tables. So formally, This is what we call the normalization theory, since we already know that if we have a relation that is not in good form, what we need to do is to decompose. So the normalization theory formalizes what we need to do if we have a relation that is not in good form. So in this part, the first thing that we need to do is to decide whether a particular relation is in good form. So yung mga criteria natin like repetition, dapat hindi nag-exist, as well as null values. Whenever we add new records, hindi dapat siya nag-exist. But in case that a relation R is not in good form, what we need to do is to decompose it into a set of relations such that each relation R sub I in this set is in good form, and the decomposition that we are doing are all lossless decompositions. Okay, note that the resulting decomposition is not necessarily just a set containing two tables, just like what we've shown a while ago, but this could be a set of relations coming from further decompositions of relations that are not yet in good form. So the basis of the normalization theory are these two concepts, the functional dependencies and the multi-valued dependencies. So let's start with the functional dependencies. And this is just a rough idea what functional dependencies are. So usually though, we have constraints or rules on the data. And for example, if we are dealing with university databases, one constraint is we have in students and instructors na dapat uniquely identified by their ID. Another example is each student and instructor has only one name. So, hindi niya gagamitin yung alias niya or any other name. So, yung legal name lang yung gagamitin ng student and the instructor. And then, each instructor and student is primarily associated with only one department. So, kahit na nag-shift siya from one department to another department, mainly, parang at a single point in time, isa lang yung association ni student sa isa department. And then, another example is that each department has only one value for its budget. And, hindi rin siya pwedeng associated to two buildings. So, let's move on to more concepts, and we're defining here what a legal instance is. So, remember na yung instance is a single snapshot of the database in a specific point in time. So, parang freeze mo yung database mo or freeze mo yung contents ng table. So, an instance daw of a relation that satisfies all such real-world constraints is called a legal instance of the relation. Okay? So, a generalization is on the second item, which is called a legal instance of a database. So, it's a legal instance of the database if lahat ng relation instances are legal instances. So, snapshot ng buong database, including all the tables, satisfies all the constraints. Then, that is called a legal instance of a database. Okay? So, yung functional dependencies are constraints on the set of legal relations. And it requires that the value for certain set of attributes determines uniquely the value of another set of attributes. So, later on, mas magigets natin yung sinasabi niya dito. And to begin with, let's recall that yung key or the primary key uniquely identifies a particular record from the set of all records. So, may kinalaman si functional dependency doon because basically we are utilizing the idea of uniquely identifies a particular. So, here's the formal definition of the functional dependency. Suppose we have a set R, and this set is a relation schema. So, you can think of this as just a set of all the attributes of the relation. And then suppose we have some alpha subset equal to R and some beta subset equal to R, then there is a functional dependency between these two set of attributes. Okay? So it is denoted by this arrow, left arrow notation. So functional dependency from alpha to beta if and only if, for any legal relations, whenever any two tuples t sub 1 and t sub 2 of R agree on attributes alpha, then they also must agree on attributes beta. So to put it simply, for any possible tuple na t1 and t2 ni R, kapag kapareho sila sa set of attributes alpha, then dapat pareho din sila sa set of attributes beta. So ito lang yung kailangan natin na masatisfy to say that there is a functional dependency from alpha to beta. So let's have an example. In this particular example, we have a relation containing two attributes, A and B. So first, let's start with, there is no functional dependency from A to B. Okay? Because in this instance, na-disobey na niya yung pareho sila dito sa A, pero magkaiba sila dito sa B. Pero hindi niya na-disobey yung B then A na functional dependency because in this example, for every possible pairs of value ni tuple sa B, magkakaiba na sila. Here in this slide, we will discuss about the closure of a set of functional dependencies. So note that given a relation, we can actually have not just one functional dependency between the attributes kasi basically we are comparing the relationship between the set of attributes in the relation. So pwedeng we have more than one functional dependency. And suppose we have a set F and it contains these two. There is a functional dependency from A to B and then B to C, and then there are properties of this particular relationship. The first property that we will see in the later slides is that it obeys transitivity. So if it obeys transitivity, then we can have a logical implication. Given that this is true, then we can imply that there is a functional dependency from A to C. So we can denote the set of all functional dependencies as F, and the closure of F is equal to F plus the union of all the logically implied functional dependencies from F, and this closure is denoted by F plus. So there is a non-trivial but very close relationship between the idea of keys and functional dependencies. In fact, if K is a superkey for a particular relation, so again, what is a superkey? A superkey is a subset of attributes of R such that it uniquely identifies a particular record. So if K is a superkey for a particular relation, suppose R, then we can say that K o yung set ng attributes in K ay may functional dependency to R. Okay? And that is vice versa. If there exists a functional dependency from K to R, then K is a superkey for relation schema. And moreover, K is a candidate key for R if and only if K is a superkey. So, pwede natin palitan yung part na to ng K is a superkey. And no alpha or subset of attributes ni K ang functionally dependent pa sa R. So, it's equivalent to saying na si K is a minimal key for R. Kasi wala nang mas maliit pa na set pa kay K such that this set of attributes can uniquely identify tuples in R. Aside from the concept of super keys, we can also use functional dependencies to express relationship between the different attributes, the different set of attributes in a relation. So, suppose we consider ulit yung schema natin a while ago, the in-depth relation or in-depth table. It is expected that yung mga functional dependencies na ito nag-hold, if the department name is the same, then dapat the same din yung building name. Yun yung ibig lang sabihin nito. If the same yung ID, then dapat the same yung building. However, we will not expect that kapag pareho ng department name, then pareho sila na salary. So, dalawa lang yung primary purpose ng functional dependencies. The first one is to test relations to see if they are legal under a given set of functional dependencies. So, given an F, which is basically some relationship of the attributes, and a set of schema or design ng database, we can use the functional dependencies as a formalization of the constraints that we wanted to enforce, tama? And then we can use the idea of functional dependencies to identify whether our design or the schema follows yung functional dependency. So, another way of saying this is a particular relation R satisfies F, or the set of functional dependencies F. And the second purpose is to specify constraints. So, we use functional dependencies to specify constraints on the set of legal relation. And yung way to say it is F holds on R. Okay. Also note that sometimes a specific instance of a relation schema may satisfy a functional dependency even if the functional dependency does not hold on all legal instances. So, nagkataon lang by chance na yung set of all records have unique names. So, may functional dependency from name to ID. So, the name uniquely identifies the ID. Pero hindi naman ito true for all instances of that relation. There are also different functional dependencies that are trivial. Bakit siya tinawag na trivial? Because lahat ng relation, regardless kung ano yung format nila or ano yung mga attributes nila, totoo yung functional dependency na yun. So, for example, we have the tuple ID and name uniquely identifies the ID, as well as yung attribute sa sarili niya. So, in general, we can say that a functional dependency from alpha to beta is trivial if beta is a subset of alpha. So, in this case, diba, ID is a subset of ID name. And also, name is a subset equal of name. So now let's connect the idea of lossless decomposition and functional dependencies. So in this slide, I'm showing that we can actually use the idea of functional dependencies to show that a certain decomposition is a lossless decomposition. The naive way of showing this is that given a decomposition R1 and R2 of R, we need to show that for all possible relations or for all possible tables on schema set R, this one is true. So, as you recall, this is just the natural join of the two decomposed tables. Dapat equal siya dun sa original table. So, alternatively, there's another way that is easier, and that is by showing na the following statement is true. So, you just need to show that at least one of the following dependencies is in the closure of F. So, this one is by showing that there is a functional dependency from the intersection of the attributes of R1 and R2 to either R1 or R2. So this is sufficient condition for lossless joint decomposition. It only works if all constraints are functional dependencies. So wala pa tayo sa multi-valued dependencies. So mas madali natin mag-gets if we have an example. So suppose we have a relation with attributes A, B, and C. And then there is a set of functional dependencies A to B and B to C. And the closure of F is technically all the functional dependencies that are logically implied from the original set F. Okay, so for example daw, if we have R1 and R2 with decomposition A, B, and BC, let's compute for the common attribute. In this case, we have a common attribute B. In this example, it is a lossless decomposition because there is a functional dependency from B to BC. This is just a shorthand notation for indicating that B and C is a member of the set. Okay. So, paano na imply yung B to BC na functional dependency? And paano napakita that this one is part of the closure of F? From the book, you can actually see that there are several rules that are used to obtain the closure of F. I am showing in this slide a portion of the book to show that there's a set of axioms or rules called the Armstrong axioms, and equal siya dito sa tatlong rules na to. It's called the reflexivity rule, the augmentation rule, and the transitivity rule. Medyo straightforward yung transitivity rule natin, and it was also shown in one of the examples before. So, if A to B holds, and B to delta, gamma, B to gamma holds, then alpha to gamma holds. So, medyo straightforward yung transitivity as well as yung reflexivity. For reflexivity naman, if alpha is a set of attributes and beta is a subset equal of alpha, then alpha to beta holds. So, in this particular example sa reflexivity rule, yung naive na reflexivity is itself. So, alpha to alpha because alpha is also a subset equal of alpha. So, for augmentation rule naman, if we have alpha to beta na functional dependency and we have some gamma which is a set of attributes, then we can parang multiply on both sides yung gamma. So, we have something like this at the end. So, ang nangyari dun sa previous na example natin is that from the original F, we can derive this one by performing some augmentation rule using the Armstrong axioms. So, we started with B to C kasi meron tayong B to C dito, and then we perform an augmentation rule. So, BB to BC, we just augment B to both sides. So, since this is a set, we have B to BC. So, we just showed that B to BC is part of the closure of this F. And since we have this, then we can say that this is a lossless decomposition, or itong particular R1 and R2 na to is a lossless decomposition. And then let's move on to the next example. For the next example, another decomposition pa rin siya of the same set. So, instead, meron na tayong A, B, and then AC. So, the intersection of R1 and R2 in this case is the set A, and the set containing A, and we can also show that A, there is a functional dependency from A to AB. So this is following the augmentation rule pa din. So instead of starting from B to C, we actually started from A to B. So from A to B, and then augment A to both sides. And then after that, since this is a set, then magiging A to AB na lang siya. Okay. So to summarize yung Armstrong axioms, there are 3 basic Armstrong axioms, and this set is sound already because they do not generate any incorrect functional dependencies and they are complete. So enough na yung tatlo na yan to generate all functional dependencies. However, medyo mahirap na ipakita yung other members ng closure. So, nag-provide ng additional rules para hindi na tedious or hindi na sobrang basic nung mga ina-apply na rules. So, we have the union rule, which is if we have alpha to beta and we have alpha to gamma, then we can say that there is alpha to beta gamma. Okay? So, since these are just sets, so we are getting the union of B and gamma. For the decomposition rule naman, we have this. So, if alpha to beta gamma holds, then alpha to beta holds and alpha to gamma holds. So, basically, dinocompose mo yung union rule dito. Okay? And then, there is a pseudo-transitivity na if alpha to beta holds and gamma beta to delta holds, then we have alpha gamma to beta. So basically parang nag-cancel out yung beta sa part na to. So this is called the pseudo-transitivity rule. And sometimes hindi na to hinihingi pa. It's okay to use this additional rules because we can prove naman that the 3 additional rules are obtained from the basic Armstrong axioms. So whenever we design a schema of the database, hindi naman exactly kung ano yung form or structure ng database at the beginning, yun na yung magiging final form niya because it could dynamically change over time. So whenever there's an update on the structure of the schema, like someone adding a column, removing a column, as well as adding new tables, we need to make sure that the new or updated version of the table follows the functional dependencies that was set at the beginning. So, testing the functional dependency constraints each time it is updated can be costly. So, it is useful to design the database in a way that the constraints can be tested efficiently. If we are dealing with just one table, of course, madali lang i-test if it's in good form. Otherwise, we need to further decompose the table such that makaka-arrive tayo dun sa collection of relational schema that is in good form. Itong part na to medyo parang may typographical error ata si Silbershatz. Pero let's move on to the next item na lang muna and then let's clarify it the next meeting. A decomposition that makes it computationally hard to enforce functional dependency is said to be not dependency preserving. So may mga certain decompositions na mahirap i-enforce yung functional dependency, and these are called not dependency preserving. So let's give an example for this. So consider this schema department advisor with function dependencies as listed below. So meron tayong I_ID for the instructor ID. So we also have the student ID as the S_ID. So yung functional dependencies niya is that in this particular schema, we are storing the relationship between a student and an instructor. So whenever an instructor participates in this department advisor relationship, inuulit yung department name where the instructor belongs. So, meron tayong mga schema na mahirap lang i-decompose. So, we can say that a particular structure of the schema or the composition is not dependency preserving. So, I guess we are ready to define the Boyce-Codd normal form. So, in the definition, we can say that a relational we can say that a relation schema R is in Boyce-Codd normal form with respect to a set of functional dependencies if for all functional dependencies in the closure of F of the form alpha to beta, okay, at least one of the following holds. So kahit na medyo complicated yung at marami siyang sinasabi, madali lang yung gusto niyang ipakita dito. Either isa dito ay totoo, and that should be true for all the possible tables. Sinasabi niya ay alpha is a super key of R, or alpha to beta is trivial, that is beta is a subset equal ng alpha. So, mas madali pa yan kapag nakita niyo yung example. So, in this example, we have the in-depth table. So, ito yung pangit na example natin from the beginning, and we are showing that this is not in Boyce-Codd normal form. In this case, we have alpha equal to that name, and we have beta equal to building and budget. In this case, the department name is not a super key of in-depth. So, may isa siya na satisfy. At the same time, hindi rin naman si alpha to beta is a trivial. So, non-trivial din yung alpha to beta natin dito. Because building budget is not a subset of department name. Okay? Pero, if we decompose this in-depth table to two different tables, instructor and department, magiging super key si department sa department table. So, it is in B, C, and F. So, given that the particular schema is not in Boyce-Codd normal form, ano yung kailangan natin gawin? It's a simple process that we just need to follow. So, suppose merong alpha to beta na functional dependency, and this alpha to beta caused a violation of the Boyce-Codd normal form. What we need to do is to get the value for alpha, get the value for beta, and then you decompose R into two tables, and yung content ng two tables na yun ay attributes ni alpha union beta, and the remaining parts of the table will be R minus B minus alpha. So, ang mangyayari if we have if we will follow the decomposition dun sa previous example natin kanina, we have alpha equal to department name, and we have beta equal to building and budget. And then, if we just replace alpha and beta with these attributes, then the first table will be alpha union beta. So, we have department name, building, and budget. And then, the remaining table will be R minus something. And yung something na yun ay, in this case, we have B ang beta natin is building budget minus department name. So, building budget. So, the rest of the entire R minus building budget. So, matitira sa second table natin, si department name pa din. So, if we will use this decomposition, then we are guaranteed that this is in Boyce-Codd normal form.